Yes, so shall I begin?
Yeah.
Okay.
Oh, yeah. Before you begin, let me introduce the speaker. Lokesh has been working with us for more than 2 years. More than 2 years, right?
Yes, sir. It's almost 2 years, yeah.
In fact, this is the first time I'm seeing him in person, right? Maybe thanks to COVID or not thanks to COVID, I don't know. And he has gotten a lot of interesting results on two-legged walking robots, bipeds. Some of the recent works are RA letters, locomotion on digit walking, locomotion walking on digit. Uh, and then there is some work on stock 2, quadruped walking using linear policies, and so on and so forth. So I thought maybe, before he goes to the US for higher studies, maybe I thought we call him here, similar to Utkarsh, call him here and have him give a talk and share his experience over the past 2 3 years. So yeah, some of you know him, some of you do not know him, right? Yeah. So Lokesh, here, all yours.
Yeah, good afternoon, one and all. And as Professor said, I'm Lokesh Krishna, and I've been working here for the past couple of years. So most of whom I worked with are not here in the lab anymore. So they had passed out to for higher studies or something or the other. So Shishi sir reached out to me to present all the work, and it was kind of not very organized. So when I was actually searching for a title, I couldn't think of a better title because essentially that's what I'm going to talk about. So the nuts and bolts of learning legged locomotion. So primarily this is important because the things that I'll be highlighting here are probably significant in practice more than the theory or the kind of hypothesis that you might have, when you write it in paper. So let me just move on a little on my background. So I'm actually from IIT BHU. I recently got my degree in electronics engineering, and in my sophomore year, I joined here at IISc with the Stoch team, which later led to a collaboration with Ohio State University, where we extended the work to bipeds with the cyberrobotics lab headed by Professor Ayunga. And meanwhile, in the parallelly in my junior year, I interned at Max Planck, Germany, where I got to work with Bolt, which was their own custom in-house bipedal platform. And once this was done, I was kind of closing my act and I was focusing on my admission. But lastly, like 6 months before, I was reached out by Professor Nidhi Sitapati, again from MIT. So she was particularly interested in the intersection of biomechanics and deep reinforcement learning for human motor modeling. So I got to work with her the last few months, which I'll be sharing now. So given all this, you might be thinking, I'll be running out of pages in my passport or anything, but when I was actually working, I was physically present just here in Chennai. So all this was remote collaboration. So thanks to COVID. Okay, so I'll just like to start with this very minor project. So I got to know an origin story is probably important for Professor Jonathan Hurst. He's the CTO of AR Robotics. So for him, it was actually a clunky humanoid that he made in his undergrad, which led to having this huge company that he's currently heading. And I think for our Shishir sir, it was a dancing robot. I don't know if many of you have seen, or at least, I mean, I don't know whether it was actually dancing. That's what it said in the video description, at least. So to me, it was. So to me, it was this robot named Gerbot. So when I was starting in my second year, I came across a motivation to or kind of natural mimicry to be done in robots, and I came across this particular desert rodent. So this is actually named Jerbova, and hence the name Gerbot. So if you observe it, the kind of gaits that you usually come across in bipedalism are walking or skipping or hopping and anything in between. But however, this gait was a very unintuitive mix of all. So that, and due to that, it had very superior agility over any other bipedals that you come across in nature. And secondly, though agility was the primary reason where we took this as our motivation, secondly, given its natural habitat, it was very well known for its endurance. So the energy expenditure was pretty minimal. So this is the kind of mimicry that we wanted to do, but again, yes. So we started with something that looked like this. So this is just a scrap put together, and we just tried to do a kinematic proxy of whatever was happening, which later led to this assembly, which was probably still a very crude version of what we wanted to do, but it was entirely end-to-end 3D printed. So with this platform, we were able to get some primitive dynamic balance. So out here, if you see the cords and everything are just for safety, but otherwise it's able to actually recover from disturbances and load disturbances and physical perturbations. Somewhere around this time is when actually COVID struck. So the platform was there at IIT BHU, and I had to go back home, so it was kind of came in a pause. But in the meantime, we had to get this platform from here all the way to here. So as a sophomore with not very acclimatized to sophisticated techniques like optimal control, I just came across this magic word, DeepRL. So it was at that time, I think, DeepMind's AlphaGo, if I'm not wrong. Yeah, it had recently won over the world champion, and all the it's all hots for DeepRL based techniques. So my thought was just very simple. If a technique is able to solve a very challenging cognitive process, such as the game of Go, can't it just learn to walk? So I just thought with this assumption, I went ahead to train, and boy, was I wrong. So I tried hours and hours to get it. And actually, this platform is not exactly RURDF. It's an open source one, and we wanted to try it out in that first. So just to get it to stand, it took us weeks, and walking from there was not even possible. But however, I held hope and proceeded with DeepRL. During the pandemic, we also had iterated one more version in simulation, that is Arjarbot beta. So it was right about this time that I joined Stoch Lab, and I got to work with some minor projects. So on the far end, you can actually see Rhizome, and that is Stoch 2. So my first project was to export the code base from PyBullet to Rhizome. So I kind of did some qualitative studies and found Rhizome to be super fast when it comes to CPU simulation. And next up, we also had ideas to integrate tower back then, which required the use of tower trajectories in PyBullet. And hence, I also developed a wrapper for the same, hence the name TowerPy. And on the far right, you can actually see the first ever exported version of Stoch 3. So this is kind of a cockroach gate that I got to work with some primitive DeepRL policies. So I'm just so happy. I mean, this code base is available, but please don't use any of them. And I'm just so happy Aditya sir never got to do the code review of it. If not, he wouldn't have allowed me into the lab, I'm sure. So after this, I got to understand a bit more into the quadruped community. So back then, quadrupeds were not a very new technology. They were actually quite established. So the results that you're seeing on the left were actually the state-of-the-art results in quadruped back then. However, they were also able to scale to challenging terrains, as you're able to see. However, this came at a cost. Specifically, their requirement on sophisticated actuators, computation, and sensors. So all of these robots depend on either one of the three. However, on the other end of the spectrum, you can actually see a growing interest in hobbyist robots, such as like low-cost quadrupeds. So on the top, to handle, to obtain reliable walking and even such low-cost quadrupeds, people came up with this kind of an automated synthesis approach. So this was first given out by Vincent's group at Google Brain. So these two papers, Sim2Real and PMTG, actually introduced us to using these RL-based policies towards automating the controller synthesis entirely, and especially in crude hardware systems like this. So we had our own version of the same. This was work by my mentor Shashank, titled Gate Library Synthesis. So we had a library of all these manuals put together, and you can see it in the hardware. However, the next logical step was to move. As you can see, these policies are doing very well in background. But from here, we had to go to a challenging terrain, and that was smooth. So that is when I kind of wrapped up my projects and jumped ship to work with Karthik. So Karthik back then was actually trying to get Stoch 2 to work on slopes specifically. And I hope most of you are familiar with this work, which was published at Corel. So I'm not getting much into the results. I'll just briefly go through the approach, and I will highlight certain aspects. So this was the pipeline. So the major difference from the gate library synthesis paper was that we had dropped the joint state feedback. So what Shashank did was to just dump in the entire robot state and try to get some form of modulation in Bezier curves, which was a very which was a very unintuitive mapping, and there is really nothing we could say about what the policy was actually doing. But what Karthik said was he just removed all the joint feedback because they were very nonlinear, and there is nothing that we could actually make out of what the policy is doing. So he removed it, and on the action side, he had removed the Bezier curves, and he had used simple trigonometric functions. So that is ellipse out here, and it parameterized in such a way that it is quite interpretable. So one way I would like to think about this idea, which probably didn't strike us back then, is that we just focused on the states that we wanted to control, which is the underactuated torso, right? So analogy that I can drive here is that it is probably comparable to the single rigid body dynamics that you're familiar with, where all you care about is the torso and you don't care about the leg kinematics or how the transition happens or dynamics or whatever. So it was very similar to that. And the states, I'll just get into the details. So the policy looked something like this. So in the observation space, we had a history of body orientations. And then we had the orientation of estimate of the support plane. So first of all, we couldn't afford velocities. So that was the real reason we just went with a history of orientation, because we had noisy IMU estimates. And secondly, though the joint space or joint feedback was not very interpretable, we still had valuable information that was being lost. So in order to bring it to a low dimensional, in order to bring it into a low dimension and still keep the interpretability intact, we came up with this support plane estimation. So given the plane, assuming that the plane is not changing between two consecutive trot steps, we were able to generate this slope estimator. So basically, in between two trot steps, we just fixed the vector and we were able to get the plane. So a more straightforward understanding can be seen from this GIF. So out here we had a step length, which was in the action space, which was just the ellipsis major axis, and then you had the steering angle, which was the angle about the yaw, and then you had the x, y, and z shifts. So though the step length and steering angle were sufficient, with the shifts, what we tried to accomplish was actually a strategy that we came across in biomechanics named telescopic strut and lever. So in quadrupeds, it's very generally found that these two strategies were widely used. So what these two strategies mean is that whether you would like to keep your leg right below your hip or try to shift it along the elevation to accommodate the terrain. So this is the major difference. So though we were aware of these two explicitly, we didn't model it. We just gave the freedom for the policy to choose from itself by virtue of its training. So with this, you can see the results that we obtained on the top. So as you can see, we can scale to these uniform slopes, up and incline, decline. And it was also quite robust to perturbations, though it was explicitly trained for that. And finally, an interesting result was that the policy directly scaled to stars by treating or assuming that it is slow. So it was kind of what I'm trying to show here is that it's just robust to that stubbing or the collision that happens with the steps. So instead of going deeper into the details or the results per se, I'd like to highlight this. So one thing that we found with ARS is that no matter what, a solution was always found. So in this GIF on the top, if you see, in theory or technically speaking, this walking down should not have happened. Like it shouldn't have been able to or walk across the decline. The reason is when we defined the step length was actually from 0 to 1 since it was length. And when you are in incline, assuming that the elevation is high and increment is positive and the orientation is also positive, if you are mapping it to 1, then naturally, when you are actually walking downhill, it will be mapped to 0. So in a way, it was our mistake and the odds were against it. But still, ARS found out a way to walk by exploiting the shift. So all it did was to do a kind of slipping where it just actively used this X and Z shifts. That was very interesting. And secondly, of course, we did domain randomization. So we couldn't actually directly do much experiment. So we had to use some techniques that are there in the literature. And one such was domain randomization. So domain randomization was very famous with neural networks. And they are also supposed to work because it's a nonlinear map and a universal value function. So it could cache these differences in the dynamics. However, when it comes to a simple linear policy or a matrix, we were not even sure that it will ever work. But the way ARS figured out a solution for this was it just averaged its sensitivity for all these feedbacks. So depending on friction, it will just try to tune or average out over the entire distribution of dynamics. Finally, the final nail in the coffin was we also added the noise in the torso orientation. So this is something we found in the hardware, and still the robot was able to go across all these terrains. To set context to this argument, I'd like to show a result that we got with PPO. So in order to do a baseline comparison, we also did this training with the well-established vanilla, so deep RL algorithm, that is vanilla PPO. So this is a fact that was reconfirmed by Utkarsh also recently. When you directly put it in our framework, for some reason, these PPO policies don't converge to a very reasonable solution, or at least not smooth solutions that are hardware friendly as our ARS. So these are a few reasons for us to bet our money on ARS, and basically for us to extend the work. So the only limiting factors that I believe for ARS to continue was in terms of the hardware. So we had something called as joint play in Stoch 2, given the kinematic linkage. And then when it comes to, of course, servo gears and impacts are not the best combination. And secondly, we had a great issue with the state estimation. It was a very primitive IMU, if I believe. So we couldn't afford to have linear velocities, and we also didn't have, reliable yacht. So with that, we moved on to bipeds. So this was when we took a step back and did a quick survey in the bipedal literature, because essentially, though they are very similar, there is this slight difference. So a guide to robotics has always been agent or research done in character simulation or graphics per se. So in this literature, nonlinear policies was very well established, and you could already see these deep RL policies that could solve these control problems very well. And not just that, since it gave a very fancy way to evade all the hard to model problems, like your higher degree of under actuation or your high degree of freedom itself, or the hybrid switching and contacts, etc., etc. People had very swiftly moved from this to fruitful utility in robotics. However, the transfer was not very intuitive. So the way that people moved from these simulators or simplified physics to actual robots was through these empirically significant techniques such as priors, reference trajectories, and domain and dynamics randomization, and curriculum learning. So these techniques, they don't have any theoretical backing. It's just based on practice that they were able to find these things to work, and there is no guarantee that you can say, this is always going to work. On the other end of the spectrum, there were also linear policies which could do similar motions. And if it were to me, I would even say it is doing a better job than the goofy motion from a bulky neural network. But surprisingly enough, there were no counter parts in the robotics community. So people were not using linear policies per se to control their pipets, at least till then. So that raised the question on whether the complexity of a nonlinear policy is actually even required for scaling bipedal robots to challenging terrains. So a hint I can give you is Reibert's heuristics. So for people who are familiar with this, back in 1980s, with just a set of linear control laws, Reibert was able to do very agile and dynamic motions. But however, the robots were, of course, designed accordingly with major simplifications. So to answer the question on why nonlinearity is even required, we came up with these three reasons. So the first is that the periodic nature of walking gaits, which is inherently present, prevents you from actually using just a linear policy to learn, like the way they did previously. And secondly, to obtain fruitful feedback from joint states, and if the action space is naively defined in the joint space, like let's say your trajectory parameters or PD targets, then this mapping becomes super unintuitive and nonlinear. So that requires you to have actually fit a nonlinear policy and not get away with a simple linear policy. So to address this, instead of learning an end-to-end nonlinear control policy, what we proposed was to decouple this into these three modules, where the linear control policy was just learned for the sake of balance. And then there is a fixed gate trajectory generator. And thirdly, we have an engineered feedback from the joint states, which is low dimensional and interpreter. So our major contribution or our directions was to have a linear abstraction of this control framework, primarily because akin to Reibert's controllers, the sim to real transfer should be seamless. And secondly, we wanted to leverage the training through heuristics, because we found the physical insights that roboticists might have to go in vain if any learning algorithm didn't allow that. So with that, we successfully extended the Coral work to bipeds. So there was no major changes, I should say. So the first thing, the minor changes included moving from PyBullet to Mijoko, simply because the dynamics was more accurate. We had a better integrator and things like that. And most importantly, we had the required files for digits in Mijoko ready. And secondly, unlike quadruped, which is most of the time statically stable, in the case of bipeds, we had to have very active balance. So for this, the torso orientation history that I previously showed was insufficient. So we had to get a kind of damping effect. So the usage of velocity feedback was inevitable. So instead of using a torso orientation history, we went on to use angular velocities. and the rest remain more or less the same. So the policy now looks something like this, where the trajectory parameters are for each of the legs, similar to coral, no big change. But out here in the observation space, we had the angular velocity, and instead of estimating it, so in the case of a quadruped, what we did was to assume that two consecutive trots will give you 4 contact points, essentially allowing you to estimate a plane, but that was not available in bipeds anymore. So for the time being, we had went with using the true data from the simulator itself. So with this policy or with this framework, when we actually start to train from scratch, the policy never worked. So the reason simply being the system was super unstable that it just fell down, and when it fell down, there is no other way for it to get back on track, given the nature of the framework or the pipeline itself. So that led us to actually think of a way to ensure that you initialize it in such a way, something like an invariant set, where the states that you visit in the first few steps are close enough to the optimal state, is at least maintained that way, so that ARS can kind of be exposed to that upright position, and then it can move on to learn to walk. So this was the idea that we had. So being an initial policy, and the reason for me emphasizing more on interpretability was because you can literally get in and tune a few things. So what we did was to write these hand-tuned heuristic initializations. So we just decoupled relevant action state pairs, and we tried to hand-tune it. So the equations are directly extrapolated from Reibert's heuristic. So let's say you take something like y shift, you try to minimize the roll, the lateral error, along with the dampening term, that is your roll velocity, right? And the only difference is that in the case of step length, we added a constant offset to actually prevent it from stomping or walking in place. So that L0 will ensure that it at least take a step and not converge into a local minima, that is to walk in place. So we initialized this with such a equation, and we hand-tuned it for some time. And I can assure you this initial state policy was good for nothing. In the sense it could hardly take a step or two, and it's eventually going to fall. But that initial few steps are adequate and crucial for ARS to actually make it more sustainable. And that's exactly what ARS did. So I'll just get to the results in a minute. But a point worth noting here is at this point, we had removed dynamics randomization because we had the actual hardware to test it. So we didn't have to give any guarantees, but rather actually test it. So we just went on to using terrain randomization, that is just randomize the slope and try to generalize or interpolate across all these discrete slopes that you see on top. So we got a policy like this, the final train policy, and these are some of the results. So we started with a 2D robot, that is your rabbit. So it is constrained to the XZ plane. So this problem was rather simple, but it gave a lot of fruitful insights in terms of the balance. So if it was not for this stick and this leg, I would have never thought of using the dampening as an equation or as a feedback for that matter. So a point worth mentioning here is that in rabbits, since the legs were virtually practically the same, they were just having this constant offset. We just learned the parameters for a single set of trajectory. So it was not a trajectory per leg, but just a single trajectory. And we just tracked it from each of the leg in an out of space manner. So with this policy was able to directly walk, and it was just, I guess, 9 parameters that we have to learn to get this walking. And the extension to digit was, which is essentially 3D, was straightforward except for 2 major things. So the first thing was that the lateral stability was even the more crucial and important than the sagittal stability. So for that, we had just extended it, and at least in simulation it was working, which is going to bite us in the future. I'll be showing in a couple of slides. And then the next important thing was the foot. So unlike the robots in which the framework had actually worked till now, this was not a point contact anymore. So essentially that means you need to come up with a strategy for your ankle. So the way we did it was to, since we assumed that we had the terrain orientation, we went on to orient the foot in the swing phase. So when you're in the swing phase, you just try to orient it in such a way that you're accommodating to the incoming terrain. And when you're in the stance, in order to keep it smooth, we just make the ankle passive. So the moment you come in contact, you're just going to roll with the terrain. So this is what we did. And we had an interesting result was that we had an inherent robustness to force perturbation. So as you can see here, we were not trained for it. So it was nowhere in the training environment. It was just an inherent robustness that came out implicitly. And the same goes for digit. Okay, so before I proceed further, all this was very good. It was too good to be true, but it was just in simulation. And when we went to hardware, as expected, we failed miserably, to be very honest. And that led us to actually do a very deeper analysis on why this is happening. So the reasons were these three major points. So the first is the solution is an overfit to the simulation dynamics. So this was the obvious answer, because every time you do learning, you're just learning in a single simulator. So you're going to, of course, overfit to that simulator. But however, the question is not why, and more importantly, how. Because when you think of a neural networks are generally over parameterized. So you have a lot of parameters. So obviously you're going to figure out, the policy is going to find a solution which is a perfect fit or a custom fit for this given distribution, right? But when you see a policy like this, a harmless policy, linear policy, how do you even expect it to overfit in the first place? So the answer was the stray terms, what I like to call non-zero stray terms. So for example, if you take the feedback of torso pitch and torso yaw, right? They are not at all relevant to an action, something like UI shift, because that control is not going to affect the previous 2 degrees of freedom. So there is no reason for them to be connected. So this hindered with our lateral stability. So that is when we first actually realized that these are stray terms and we don't exactly need it. So the fix was to maintain sparsity by learning only for the parameters of the relevant and related state action pairs. So secondly, blind tracking of trajectories was inadequate for hardware. So what I mean by this is that in the stand space, in our ellipse, what we had was a straight line. So we just used to blindly track it using PD tracking. However, that was inadequate to maintain balance, because when you do that, you're going to eventually topple in your hardware. So what I'm trying to highlight here is what the linear policy found to work in Mijoko was more of a template motion than a very reactive controller. That is to say, it's a more intuitive way to think of it. It just learned a family of trajectories, open loop stable trajectories that work for a single dynamics, that is Mijoko, rather than learning a closed loop stable controller for a distribution of dynamics, right? So I hope that is probably the crux of why we failed. So it just learned one open loop trajectory which can just infinitely walk in Mijoko per se. So the fix here was to again do domain or dynamics randomization. But as I highlighted earlier, there is always a trade-off between performance and generalization when you do randomization. So that is why we took an alternate route, that was regulations, which I'll get in a bit. And third issue was rather straightforward. It was just the control frequency was much higher, so we just reduced it and retrained it, as simple as that. And so these were the real reasons for the failure, but I'm also obliged to mention the reasons that were not. So we didn't ever have a problem with state estimation. So since we are working with Digit, which was an industry-grade robot, the inputs were actually smoother than usual. And secondly, the joint PD tracking quality was impeccable. So we didn't have to think in the direction of actuator motor model, transmission, or whatever. So with this, I'll also like to highlight a little bit on the code updates that we did for better practices, which might come handy later on. So given that those three were the reasons, we first tried to localize the training to just these parameters that are relevant. So the reason is actually something that was of necessity. So I didn't have enough compute to actually run, or I didn't have enough clusters to actually run multiple experiments in parallel. We just had a couple of PCs. And given Digit's complex model, it was a high fidelity model. So it takes a lot of time to train. It took me the order of a day or two, right? But I had to continuously fight with PhDs here for putting my jobs. And so I had to figure out a way to just get this over with. So the real bottleneck in the pipeline was that the policy evaluation between two updates was taking time. So what I like to highlight here is, let's say there are 5 different slopes, and let's say there is a policy K and K plus 1. So the way you can compare the performance between these two is only if you keep the question paper the same for both. Like if you change the questions, then you cannot say whether the policy itself has degraded or whether the task was just complex enough. So we had to kind of have a proper set of tests so that all the policies are equally being evaluated. So this was actually the step that took the most time. So let's say I'm training on a set of 6 discrete or 12 discrete slopes, then I'm going to run 12 different tests in the same code. So that was taking a lot of time. So I just simply parallelized it. And finally, as I mentioned earlier, instead of learning for all these stray terms, we localized the search to just the parameters that we thought was relevant. And by relevant, we just mean the actions that can actually have an effect on the degree on the degrees of freedom. And secondly, an important thing that we went on to do was to use height maps. So I'd also prefer height maps over discrete STLs any day, because you're going to get the terrain data as an inherent thing. So that led to the final act that was submitted and accepted at ICRA. So we had the regulations intact, and additionally, previously we were doing pseudo-blind walking. Now we actually had true blind walking, thanks to the FK-based slope estimator. So the way we ended up estimating elevation in digit was using forward kinematics. So we had a framework named Frost, where you just feed in the URDF, and you're going to get out the FK equations. So given that we chose to keep our ankle passive and roll along with the terrain, so the moment you are you're passive and you're along the terrain, you can simply use your forward kinematics to estimate the terrain. So that is how we built this estimator. So, and then, as I mentioned earlier, we added a couple of regulations that also an ankle, which I'll be explaining in a bit. So I think I've covered everything. Yeah, so the policy that was submitted to ICRA looked something like this. So the first major change was the difference in action space. So I didn't have to learn 10 or a specific trajectory for each of the leg. I just can learn a set of parameters that is a single trajectory, and I can do a symmetric transform between the two legs. So that kind of made the size of the policy into half. And secondly, we added velocity terms, error in velocity to be more precise. So this was because we wanted command control policies and not blind walking forwards. It was not at all of any use. So these are the two major updates we did, and went on to train once again. And yeah, a peek into the gate controller. So in the stance phase, what we did was something called as a torso regulation. So for people familiar with Dreibert's heuristics, it's just the same. So what we try to do is the moment your stance leg comes in contact, you try to balance the torso just using the hip motors. So try to keep it upright. And as I said previously, in the stance phase, your ankle is going to be passive. And in the swing phase, however, apart from the shifts that your policy is doing, we try to keep a active ankle joint. So we'll just try to orient it to again accommodate the underlying terrain. But the only difference now is that the data of estimation comes from your stance leg. So you estimate using your stance leg and use that angle to actually orient your swing leg. So this is how we did it. With this, the training pipeline looks something like this. And yeah, a point worth mentioning is that it's a sparse structure heuristic. So essentially, the heuristics was not in hand tuning, or it doesn't depend on the absolute value of these individual gains. What was the heuristic was actually the structure. So you can see the sparsity now. All these white blocks are nothing but 0, and we just learned for those selected pairs of parameters. So this was actually a question raised by one of the reviewers in Rebuttal, like if you're hand tuning it, what's the point of even learning it? So we then showed that you can even initialize with a random policy, but as long as the structure is intact, you'll still be able to get policies that can walk across all these terrains. So the training was done, and you can see something like, something like this. So moving on to the results, again, I just trained in slopes, much similar to the IIROS work, but I just trained on uniform slopes from -13 to 13, and there was a very good interpolation between -13 to 13 and an extrapolation from 13 to 20 degrees, which was really interesting. And what was more interesting was that the policies showed zero-shot generalization to arbitrary slopes. So that is to say, you don't need the flatness of a uniform slope to actually be successful, but you can just put any arbitrary slope, and as long as the terrain is continuous, you're still going to be able to walk. And finally, the most important reason for us fighting with linear policies for a year was this, the direct sim to real transfer. So very similar, once all the modules were in its place, much similar to Reibert's heuristic, you were able to directly transfer the policy from the simulation into the real world. So here we were able to test it up to 11 degrees. So the limit was again from the treadmill and not the robot. And a point worth mentioning is that this walking was an outcome of just learning 13 parameters. So the matrix just had 13 parameters that needs to be tuned. So I could get these results in a matter of 6 hours on a 6-core or an 8-core PC. So moving on, around right about this time was when Oregon State, which was actually the makers of this very robot, they came up with this outlandish result where they showed blind walking on stairs. So until then, stairs was not in the paradigm of proprioceptive walking. So you cannot blindly walk on stairs, and there is no reason to do so. But those people came up with such a outlandish and robust policy that it literally walked over stairs. So that was a cool new challenge. And as I mentioned earlier, one of the primary motivations for us or contributions is in a way to integrate heuristics. So that was a good challenge for us to try. So when you look at stars, at a star, it's going to be a discontinuous terrain. So unlike whatever terrains you saw earlier, the continuous ones, you cannot completely characterize them with just the elevation. So we needed to come up with a better way to handle it. And we just took the naive approach where we thought it to be terrain uncertainty and nothing else. So there was no feedback of terrain elevations. As you can see in the respective columns in lambda and alpha, we didn't do any connections. And the only strategy we can think of to walk blindly, in very much how humans do, is that let's say you're walking in pitch dark on a stair. So what you do is the moment you collide with the stair, you just increase your step height. As simple as that. So that was the strategy we wanted to encode. And to do that was rather simple because I just had to connect this feedback. That was the error in the heading velocity to the z shift. So the moment there is a collision, there is a spike in your Vx heading velocity, and then your z shift is going to increase. And that's exactly how it worked. So in simulation, we were able to get results of up to 20 centimeters, whereas in hardware, given the limitation being the logistics of outdoor experiments, we were able to get up to 7 centimeters. So these are some miscellaneous tests that we did. So on the top right corner, an interesting result was that we were able to switch from one policy to other. So this was a proof that you can actually generate a library of these policies and seamlessly switch from one to other. And secondly, of course, the perturbation results were intact to whatever we found in the simulation. And on the left bottom, you can actually see it walking omnidirectional, so forward, backward, turnabout axis, lateral, and everything. And we also got to take it outdoors, so where the elevation, friction, no condition, nothing is known. So that is the significance of this experiment. And we're able to get it to walk quite robustly. So it's definitely, I should mention here, every time I see this result, I get guilty because I'm supposed to be the one who should be pushing the rig. But since I was here in Chennai and the robot was in Ohio, the professor ended up doing it. So it's actually Professor Ayam. So when we had ICRA deadlines, this is him literally pushing for ICRA. So we got the results right on time. And yeah, for the sake of reliability, we're able to run the policy continuously without any human interference on a wide range of velocities from 0 to 0.5 meters per second. So yeah, the idea that I was mentioning right before, that a family of trajectories can be very clearly seen here. So the policy actually doesn't learn a single ellipse, but it learns a family of trajectories which it very actively modulates on the go. So that is seen by the limit cycles on the top. And on the top right corner, you can actually see that it's just not converging to these nominal trajectories, but it is also learning recovery behaviors. And finally, a very interesting result that we found was that though it is intuitively straightforward that linear policies are computationally energy efficient, we also did cost of transport analysis with our work and the baseline work, which was from Guillermo et al. And even in the mechanical energy aspect, we were able to get lesser cost of transport. So that concludes my work here. And I went on to I just handed it over to Raghav here. So once the walking was done, we had to move to more athletic behaviors, which looked like the logical next step. So that was the work taken over by Raghav. I won't spoil much of it because he himself has a lot of the technical details that goes under the hood. But on a high level perspective, what we found was when we move away from walking, the ellipses were pretty limiting. And when we tried a couple of different experiments, we just played with the face and tried to get hopping, but those were unsuccessful. And when we went about to a wild goose search to find a trajectory that suits hopping, we were not able to find one. Instead of a trajectory, we interchangeably went on to use a reduced order model. So the framework currently looks something like this. And so where we have this component of a reduced order model in which we can have a description of the motion that we want, which can be hopping or skipping or whatever, or even transient behaviors, which can be an outcome of a trajectory optimization that you can do with that model. And what we realized from our previous results was that apart from the modulation, the rest of the terms are nothing but feedback terms. So you can kind of sandwich the reduced order model with these feedback terms on one end, and on the other end, instead of modulating the trajectory parameters, you can simply modulate the parameters of the reduced order model. So the policy essentially is learning both of them together and trying to get a consensus between both of it. So one way to think of it is like we are doing online system identification depending on the state. And then the rest remains the same. So given a behavior description and this sandwiched approach, we should be able to get it. So after a lot of struggle, I should add, he was able to get this to hop. He was able to get these results in simulation. And the policy looks something like this, where each of the color bands here are nothing but the phase. And in orange band that you're seeing is nothing but the model parameters, and we use the slip. So the only parameter that we wanted to learn was this stiffness constant. So apart from system ID, additionally, this full order dynamics is definitely different from a reduced order model. So it's one of the reasons we wanted to keep it as an active feedback, so that in different modes, if the reduced order model itself changes, like say, for example, when I'm landing, I want a much higher spring constant. When I'm taking off, I need a much higher spring constant than when I'm landing, right? So we wanted that kind of behavior for the policy to itself learn. So that is why we added the stiffness constant. I'll just quickly show you the results. So these were some of the preliminary results that we did. So let me just wait for a couple of seconds. So it might look as if Guillermo is holding it, but in the last two hops, you'll actually see that he's not. He's just trying to keep the hand close enough because it costs 75,000 USD, and more importantly, something broke. Even a small screw, right? It takes us a couple of months to hear back from Agility Robotics. So yeah, here you can see that his hands are actually not intact. He's just doing some precautionary measures. So this kind of compiles my work here with linear policies. I hope some of the practices are still relevant since we are into linear policies. So right about this time, I actually came across these platforms in my junior year. So these, I would just say these are platforms baked with agility. They are super lightweight. You can throw them in the air. As you can see, this robot on the right was able to almost hop 5 times its body height. And they were also having a biped, which is my true love. So I just had applied them to work with Bolt and get these parkour-like behaviors. So I was accepted in as an intern in my junior year, and this was the idea that they were more interested in, like that these were kind of the check boxes that they wanted any of their approach to fulfill. So the first being they wanted purely state-based control. So that is very similar to what you might see in an MPC. That is to say, if you see the RL architecture, people often have a notion of a clock or a phase variable that is actively ticking, and it is sent as an input to the policy. So this was something that the lab was very against, particularly because it's quite uncertain on what these clocks actually mean when it comes to making and breaking contacts. Let's say, for example, you're doing a kind of jump or a maneuver like that, there can be early contacts, right? So these research didn't actually make sense. So they wanted a pure state-based control in the RL literature as well. Secondly, they wanted to modulate behaviors from a single demonstration. To explain this better, so this was a work that was published last year from Kaushal Shina's lab, Professor Kaushal's lab. So here they have a humongous nonlinear policies where they actually feed in trajectories from a gate library. So they have n different behaviors, and in order to make those behaviors come true, basically use a controller, they feed those trajectories into the network itself, which actually makes the network super big. And they need, for even the slightest change in the velocity command, they need a new trajectory. They have to generate it offline. So this is something that we were totally against, and we wanted to just use a single demonstration and come up with a way to extrapolate its performance. So for example, let's say you have a demonstration for a single velocity. Is there a way to extend it to a bandwidth of velocities? And secondly, for like the style of task, let's say you have a trajectory to know how to hop in a certain way. Is there a way for me to play with the framework for me to extend the behavior to a different style of task? And finally, last but not the least, they wanted a cleaner and a very general framework. So they didn't want any event-based or mode-based switching or different controllers that are just being activated based on our insights on the task. They wanted one policy should be able to solve all of it. So at this point, a work that was rolling out of the lab was from Miroslav. So what he proposed, it was greatly motivated from this work, deep mimicking graphics. However, the only major difference that he did was to decouple the training process. So in deep mimic, what they did is they always have an imitation term and a task term, and they are together, and they work in consensus, and they do the training. But what Miroslav suggested was to decouple this training process and have two stages. So in your first stage, you just try to cache the trajectory motion in your policy. So what we do is simple imitation in ideal settings. So we just try to, instead of having a time-based trajectory, we just have a policy which is able to do control in ideal conditions. And once this policy has been done, we move it on to the stage 2, where we try to extend it to all these new behaviors that you'd like. So we'll have a simple reward, a task reward, which ensures that there is no local minima, and it goes to learn standing alone. So the behavior from stage 1 is still intact, but you'd like to add on more features, like let's say different velocities, or let's say change in terrain, things like that. So with this two-stage approach, he was actually able to get these results in Bolt. So no matter what, this platform can just go on hopping. So this is again a spongy terrain. The robot simply doesn't care. And then you have these perturbations. So these might look small, but the robot itself is about 20 centimeter, and these platform perturbations are about 5 to 10 centimeters. So they are significant when you count the robot side. So my job here was to extend it to Bolt or get similar results. So that is when I actually got into using these deparallel based techniques exclusively for Bolt. So I started with using from this far corner where there was almost no imitation. So people who had worked with deparallel might know the initial results look nothing like what you want. The algorithm is just going to exploit it some way or the other because you've underspecified or either underspecified or overspecified it. So a quote that comes to my mind is something that Pulkit Agarwal recently mentioned. So machine learning is actually super good in finding answers, but the real problem is we don't know to ask the right questions. So that is exactly what I was facing. So as you can see, though there was a trajectory and the imitation reward was straightforward, it still looked nothing like what I expected it to. So the reason was this third point, which was actually that we defined the full state. So what happens is because of the translational invariance, as you linearly increase, this x position is just going to increase. So that kind of threw our policy way out of the nominal trajectory. And secondly, it made it very sensitive to the initial conditions. So at certain initial conditions, you can see the policy to be working out here. Like the green is actually the visualization of the trajectory, whereas the gray is the actual robot. But it just is super sensitive, and in other initial conditions, it simply fails. However, interesting result that we found here was that this trajectory was from an older version of Bolt. So this was an error that I hadn't found. So the trajectory was from an older version of Bolt, and we had a hardware update, and the model was actually a newer version of the Bolt. But still, though it was dynamically inconsistent, we still were able to get this kind of a walking behavior. That was promising because the physical feasibility of the trajectory was not a dependency for the policy. So moving on since there were a lot of moving parts, I freezed it and I got trajectories. Since we had an in-house MPC for Bolt, we got the trajectories from MPC, which for a fact we know works. And we did imitation on it with this updated state space. That is, we just removed the basics and we were able to get this behavior. So again, the imitation was impeccable and it was visually also perfect. And once we had figured out every other nitty-gritty details, we then went on to using trajectories from a trajectory optimization, a Kinodyne planner that was in-house on that lab. And as you can see, you can see this very natural wavy walking, which is probably much more challenging than that robotic walking that you see here. But along this process, something that people often oversee and is probably the biggest tedium is to tune these environment parameters or reward gains. So it's highly debatable. Like we try to go from this model-based paradigm to model-free just to get over this tedium. But however, in model-based, you just try to get with your model and tune those things. But in model-free, you ended up doing the same for your reward gains any way or the other. So, however, that was inevitable, and that was a major observation that we made, and we were able to get the stage 1 results. So, as I mentioned earlier, with this stage 1 as an initial policy, we were able to extend it to stage 2, where we try to robustify and kind of blow up to generalize to different behaviors. So, in both of these trainings, what was common was the simple task reward, that is the base stability reward. So, we tried to minimize the roll oscillation, pitch oscillation, and the base Y oscillation. So this was all that is required to ensure that the stage 1 policy does not diverge from what it learned in the previous stage. So this kind of characterized walking sufficiently enough. And apart from it, we did these 2 set of experiments where initially we just played with the random initialization to robustify or to learn recovery behaviors. So if you observe it carefully enough, you can actually see the moment we deploy it, it takes a dip or that's kind of a recovery behavior. And on the other hand, we did terrain randomization. So where there were height differences up to 10 centimeter, and you can see these sinusoidal octaves. So point worth mentioning here is, unlike our previous work with a digit, there was no terrain feedback at all. So all we had access to was the proprioceptive feedback. So the only thing the policy can learn is once the impact has happened or once the depression has been faced, how to recover is all the policy can learn. Still, stage 2 was successful, and we were able to extend the stage 1 ideal policy to these unseen conditions. So 2 major observations that we made here was that there was no catastrophic forgetting. So this is something that is very familiar to people who might be using PPO. So your policy will be learning something, but the moment you change curriculum or some context, it'll just start to unlearn, like whatever it has learned. That is something that was not at all happening in this two-stage process, because though the reward functions are different, they kind of complement each other. So this local minima is kind of averted. And secondly, this is again debatable statement, but since I've decoupled it, I didn't have to worry much about the reward tuning. It's a tad simpler because you don't have to worry about the relative weighting. So it makes your life a bit easier. So from this, again, as I mentioned, the next step was to try to get a velocity control policy. So with the stage one policy, where we just tried to imitate the exact trajectory, we went on to generalize or blow it up to any arbitrary velocity. So in stage one, we just try to imitate the trajectory. So let's say there is some walking forward and backward, then that's exactly what it is going to do. But in stage two, we want to kind of make it decoupled from that time dependence. So what I mean is, in this first training, if you see, what we did was to use the exact same velocity commands that were consistent with the trajectory in which it was generated. So that's just a time dependent velocity command, and we're able to get the walking. But however, the moment we gave some arbitrary command to this policy, it just failed. So instead, we just trained with arbitrary velocity commands and a velocity tracking reward, and we were able to obtain these results to moving forward, backward, left, and right. And again, the point I'm trying to highlight is that the coherence between your trajectory, the time-dependent trajectory, and your policy has been broken now. So it's just purely state-based control. It just depends on your velocity commands and can move in omnidirection if you want. So that was again one of the primary things we wanted to accomplish. But however, this was though the policy showed very good interpolation. So what I mean is the trajectory that we used for this specific experiment had velocities up to plus or minus 0.2 meter per second. So you can see this very clean velocity tracking. So that means the interpolation is really good, and we can do arbitrary commands. But however, when we move to velocity greater than 0.2, the policy simply learns to filter it out. It basically learns to ignore. So though I'm applying the command of 0.4, it simply learns to walk in 0.2. So though this pipeline was really good at interpolation, it was not able to extrapolate to higher velocities. So this was a major limitation that we found. And moving on.
When you say trajectory, what trajectory? Trajectory of what?
So trajectory, this exact motion was actually first obtained from a trajectory of images, or from a planet. So the like in the stage one, the green things that you see is actually a visualization of the trajectory.
Okay, so and then you imitate that.
Yeah.
Okay. Imitate the actions.
We just try to mimic the states. We don't care about the actions. We don't use the torts given out by the planner. We just try to imitate the states.
So you try to track.
Yeah.
So there is time dependency there.
There is time dependency there, but we are breaking it in stage two.
Okay, so how are you doing that?
So in stage two, once we added these velocity commands, so there was no time dependence in the sense you can arbitrarily change the velocities. So it need not necessarily be consistent with the velocity transitions in the trajectory. So all it requires is the current state and your command, and it can simply walk in any arbitrary direction.
Okay, what is the state and action?
So in state is just the robot states, sir, except for the basics and then your velocity commands.
Basics.
Yeah, and the basics is not there. The rest are there. The joint angles and your usual.
Y is also not there.
Y we had. In certain experiments we had. In certain we didn't. I think in this we had. Y we had.
Z also.
Z also. Yes, sir. Y we had.
And contact measurement?
No. It was just proprioceptive in the sense there was just the joint angles, velocities, and your torso state.
And angular?
Torso state. Torso states, yeah.
And your action is what?
Action is, yeah, I forgot to mention. So we actually first started with tort policies, but though it was very easy to learn those policies, we couldn't transfer it in any way. So we had to move to joint trajectories, similar to what organ people are doing. So it's just PD targets.
Oh, so you have a trajectory there. Your action is a trajectory.
Yeah, it's the set points for the PD, yeah. But it is entirely state-based in the sense it's not going to be consistent with the trajectory. It will not necessarily be consistent with the trajectory.
How many points?
I don't know which points.
Trajectory, how many points you have? How many PD targets?
So the initial trajectory that we obtained from the planner, you have.
No, action will give you a trajectory.
Yeah.
Right.
No, action will actually, so it's going to be the current set point and that's it. So depending on my state, I'll just give the targets to my joint angles and that's it. So it's not essentially like what Guillermo did, where you had trajectory parameters and you have a full trajectory. It's just a single set point at the current time. That's it.
Joint positions, basically.
Yeah, joint positions basically.
That is your action.
Yeah.
Now, how are you trying to track this, imitate this trajectory using cloning?
Yes, sir. So the reward function is very similar to what they did in deep mimic. So we just try to do.
It's okay, RL based imitation.
Yeah. So in stage 1 we imitate, and with stage 2 we try to just basically generalize it across either through commands or through terrains, which are contexts that are not at all observed in the trajectory.
So the reward is some cost which will reduce the gap between the two.
Yes. So in stage 1 that is the reward. In stage 2 we have a simple task reward. I mentioned here. Yeah. So in order to ensure that the policy doesn't actually forget what walking is, we just have these stability rewards, and that was found to be sufficient. And apart from it, we just add any other task reward that we feel is relevant. Like in
but do you go back and forth? Stage 1.
No. Once stage 1 is done, then we go to stage 2, and that's it. There is no iterative.
Stage 2 it's able to learn that.
Yes.
How big is your neural network?
It was just a 2-layer network with 64 neurons per layer.
Each layer.
Densely connected.
Fully connected?
Yeah, it was fully connected. We were thinking of using RNNs at some point, but there was there was no requirement. We tried to keep it minimalistic, and it was straightforward there.
So if it's only proprioception, joint angles, and and it's able to walk on that adapter.
Yeah. So that was. So I tried discontinuous terrains also, in the sense with sharp edges. That was found to be a little more challenging for walking. But however, in a couple of slides, I'll be showing you that when we got to hopping, we were able to even handle those terrains. But for walking, we were just able to build on this continuous smooth terrains.
But so in your stage 2 rewards, how are you ensuring that it is going with a constant velocity?
Yes, sir. So here, I think I'll show the next one. So along with the base stability rewards that you see here, which was just blindly walking forward, we add one more term, which was your velocity tracking reward. Basically, minimize the norm between it. So that was the first step, and then we extended it to this.
Oh, there is a stage 3.
No. In stage 2 itself, we added. So it was not a separate stage. We just added that reward term with the base stability term.
Okay.
So the real reason that I signed up to work here was actually to get parkour-like motions, and almost for a year I'd been just doing walking, just trying to getting restless. I wanted some behavior that looked like parkour or something agile enough. So finally, after a lot of begging, he gave me a hopping trajectory. He wanted me to pursue further in the walking, but I got to get this one hopping trajectory. So in this example, you can actually very precisely see that why a timing-based input might be relevant, or if we are still dependent on a time-based trajectory, we won't be able to exactly follow the motion. So in stage 1 of hopping, as you can see, the trajectory is very different, and the controller had to move significantly different from the contact faces in order to make it feasible in pipeline. So that was the exact time imitation in stage 1. And in stage 2, the task reward looks something like this. So the base stability still is intact. But apart from it, to characterize hopping, we just had to define this sparse reward, where if the height is within this h-min to h-max, we gave it a value, else we just gave it 0. So with this simple reward, we were able to get hopping of up to 1.5 times the body height, so on the top. And we were also able to do terrain randomization of steps plus or minus 5 centimeter. And as I mentioned previously, these bots are about 20 centimeters, so that's significant enough. And an additional thing we had to do in hopping was to penalize the contact. So the policy very easily learned to hop, but they were close to useless because the impact was super high. So to prevent it, we just had a contact penalization, and that was the policy that we eventually tried in the hardware. So compiling all led to this final work. So we wanted command control and given behavior, either walking or hopping. And we wanted the policies to be able to handle terrain or contact uncertainty, as shown by this map. And finally, one battery of rewards that I have not mentioned until now, which was crucial, was the hardware transfer quality terms. So that is to say, apart from your task rewards, which is your base rules and pitch stability, and some specific rewards for that characterize your behavior, let's say hopping or walking, you also had to have this battery of rewards on the top, which ensured that the transition from sim to real is rather straightforward. So for first, we had to do friction randomization, which is very nominal. Secondly, we did contact uncertainty, that is to rise these height maps from a height of 0 all the way to the maximum height that you actually see. And this C and D, the point C and D are something unique to our work, which was terms that ensure torque smoothness, not by any form of filtering, but actually being in the cost itself. So this torque smoothness is nothing but trying to minimize the norm between your current torque command and next torque command, or basically your history of torque. So we try to smoothen it. So this torque is actually not even a direct outcome of the policy. You have a layer of PD. Still, the policies learned set point command such that the torque was smooth enough. And secondly, it's not just sufficient if the torques were smooth, because there is no way for us to actually ensure that it's happening in the hardware. But we also wanted the actions to be smooth. That is, the set points or the outputs of the policy should also be smooth. So we try to again minimize the norm between the Q targets, ensuring the trajectories that were given out were smooth enough. And of course, as I mentioned previously, we just penalized heavy impacts. So with this, you can see the results that are being played on the right. So we're able to get velocity controlled hopping with uncertainty in contact and with all these hardware quality terms intact. So I don't know whether it already went in a close view. You can actually see that the way the foot adapts to this uncertain terrain. So it's purely blind. It just came in contact and it's reactive to the environment. So nothing else is going on.
What about hardware?
Yes, sir, I'm getting there. So yeah, with this we are doing all this, and here are the plots. So this was smooth enough. Like I don't have the comparison plots without the smoothness terms. So again, as I mentioned, there were no filters, no averaging, nothing. It was just an outcome of the reward terms that you had. These are the PD targets, and these are the robot states. And to have a quantifiable.
PD targets.
Sorry, sir.
PD targets.
Yeah. I didn't get you.
PD targets.
Yeah, the output of the policy.
Desired
What are the
position.
gains?
Desired position.
No. We decide set points. So the gains are fixed. I just send out the target joint angles. Target joint angles. Yeah. Yes. So to have a more quantifiable comparison, we looked at the phase portraits of this system. So when we remove these hardware quality terms from the equation, that is randomization, contact uncertainty, and torque smoothness, you can actually see that the phase portrait is quite jerky and it's not exactly hardware friendly. When we first put it in, we were almost close to breaking one of the legs. So that happened. And with these hardware terms, as you can see, the quality of the phase portraits are much smoother, and the trajectories that are come as an outcome are much more hardware friendly. So an implicit outcome was, again, it was robust to perturbations. So given that we had a very sensitive velocity reward term, by just observing the difference in the velocity, the policy was able to adapt. So with all this, we are parallelly doing experiments, and we got some preliminary results. But however, it was already a year, and I was in block in Chennai, and it was the right time we had second wave. So I was testing people's patience when I made them do my experiments. So given that I had to stop it, so with the preliminary results where we just got one step or one hop, so that's how we had to end it. So if I had gotten to go to Germany, probably would have continued, but yeah, we had to stop it. So this was all the results that I had worked with in Bold. By this time, I had done my junior and I was entering into my final year, and I stopped all the things that were interesting, and I was doing the boring stuff, admissions and essays and things like that. So after all that was completed, in December, I was reached out by this professor who was actually a biomechanics professor, who was not a roboticist. So she works in biomechanics, and she was particularly interested in the intersection of cognition, human motor modeling, and emerging deep RL techniques. So for this, what she wanted me to collaborate with is to.
How did she approach? Email?
Yes, sir. She just mailed me. Apparently, she had seen our papers, and she just mailed me saying that, yeah. So the primary reason I was reached out was
to Stoch.
Yes, sir, of course.
See, remember, MIT is reaching out. MIT, right?
Yes, sir.
MIT is reaching out.
So the primary reason was, again, our papers where we used Mujoko. So what she actually wanted to do is these people who work with biomechanics are very keen on using motion capture and data from actual humans. So when I actually started working, more than getting a controller that works in any system, they are more focused on why a human walks or how exactly he or she walks. And for that, a primary tool is using motion capture. So what she wanted me to do was to get some form of a rigid model, which is a perfect fit given this cluster of data. So in a way you think about it, it's very underspecified because a human is like one continuous piece, and I cannot put sensors into him to know these are the joints. And of course, humans are known to be very redundant with their actuation. But from here, she wanted to get into a rigid body space where the redundancy has been removed and there is no deformation or effects being studied. And secondly, the state of the art or what the community was actively using was a platform named OpenSim, which uses muscular models. So she was against it, and she wanted to still use nominal revolute joints and torques directly instead of muscular actuation. So for her, Mijoko was a much better choice. So that was actually the work that she wanted me to do. And secondly, her recent results that she got in reduced order models, that is this telescopic leg model, she wanted to extend it to higher dimension. So what they showed here is that with this reduced order model, they were able to recreate some of the transient behaviors that humans show. That is, let's say you're walking on a split belt and or a treadmill, simply put, and you immediately change the velocity. The way the people adapt is probably in the short horizon, it's not energy efficient, but in the long run, they try to come up with a strategy that minimizes metabolic cost. So this is what they proved with this simple telescopic system. But however, this reduced order model is not the complete story. So she wanted to study it further using high dimensional model. So yeah, and I wanted to integrate both. So both required the development of a framework. So this is what the framework that I developed for them. So given these blue points that you see are all the data that we need from the motion capture, and the rest of all is taken care by this framework. So given a nominal model, that is the human model that you can see, and the motion capture data, we came up with a heuristic technique to do automatic scaling. So once you just feed in your data and you say, okay, these are the markers present in these certain links, the module automatically scales it and makes it kinematically and dynamically consistent to the subject, accurate enough. And then additionally, we give the graphical user interface to account for any asymmetry. So the problem is, since humans are the ones who are conducting these experiments, the position of these patches are prone to error. So that can have drastic effects when you compute something like inverse kinematics or dynamics. So to accommodate this, this is something that is not found in any other framework, we developed a GOF-based approach where if you see some kind of asymmetry or some kind of error in the experiment, you can edit it visually using this module. So once this is done, we went on to compute the kinematics, which was relevant data for them to proceed with the analysis, similar to what they did in the reduced order model. So for the kinematics, I had just written a least squares, it's as a least squares problem. So more accurately, it's nothing but post-fitting. So given these endpoints on the experimental data and the endpoints on the hardware, I just try to fit it. And once the IK solutions were done, assuming the contact model of Mijoko inherently comes on like with an analytical solution for the ID. So given the contact model, there is this analytical equation of ID, and instead of using that contact model directly, we just said, so we got the GRF ground reaction forces from the data, and we obtained the inverse dynamics. So this again here, the assumption is that the data that actually created, sorry, the model that actually created the ground reaction force was something exactly what has been modeled in Mijoko. So here are the visual results, how visible they are. So from raw data, we were able to get these human models to walk, and they're actually not in contact because this is just a kinematic solution. And finally, we went on to get the dynamic solution by applying forces. So once this pipeline was ready, this is all they needed to do the analysis to fit predictive models. That is the current work that is happening. And yeah, these are just the phase portraits and torques of the inverse dynamic solution. So a point worth mentioning here is that though Mijoko had this inverse dynamics, it didn't account for the underactuation. So what you're seeing here, that is the torques of the legs are just half the picture. So when you actually try to call the function in Mijoko, it just doesn't give you these torques for the joints that are actuated, but it also leads to these phantom forces that are to be applied in underactuated parts. So it was not very feasible. So from here, we had to develop our own optimization. That was one direction. Or we are directly going into obtaining controller. We can also use deep RL. So that is the direction that is being currently pursued. So with this, my work came to a conclusion. So yeah, I think with that I'll wrap it up. So it's just, I think, as advertised, the nuts and bolts of whatever I did, the nitty-gritty details which are often overlooked. So with that, I am particularly excited in these three directions, or what is called the state of the art. So first and foremost, this was a demo that I saw in ICRA 2020. This was Marco Hetter with his platform Animal. So you might have seen this recent work. It was, I guess, a few months old, where they did massive parallelization and they were able to get RL policies to walk within the order of 20 minutes. And it has been just a few months, and Marco Hutter and his team comes to ICRA, and they're able to do the same in the order of seconds now. So he just switched on it in front of all of us, and he just did the learning. And in the order of a couple of minutes, the robot, from not knowing anything, that is essentially scratch, it learned to walk. So this means the computation pipelines is super fast. So I'm particularly excited in knowing whether it is time to actually do real online learning. So when I say online here, I'm not referring to the online interactions that generally RL people say when you have the environment, but rather online as in when your robot is online, the new strategies or split second decision strategies that you actually need to adapt. And secondly, these are all, there is a huge list of simulators that kind of work well hand in hand with RL. And particularly this direction, that is Dojo, a simulator that is from Professor Zachary Mansis's lab, is also looking towards differentiable physics. So that is generally in RL, we just do black box interactions with the environment. And the reason for deep RL generally being sample inefficient and often fragile to hyperparameters is because we don't actually have the access to true gradients, but we estimate it, which is super noisy and has high variance. So if we have access to these two gradients, does it mean we can also have improved RL algorithms to leverage this gradient info? So this is another direction I'm particularly interested in. And thirdly, as shown by Boston Dynamics for the last few years, the state of the art is currently trajectory optimization meets MPC. However, in this pipeline, this tightly made pipeline, where exactly is the place for RL? So is it in the planning phase? Is it in the control phase? Or is it in the intersection? So this is something I'd like to explore in my future work. So on that note, yeah, so this is something that has been my motivation for quite a while now. So much similar to what DeepMind did. So what DeepMind did was to kind of simplify the requirements of AGI into these games or Atari games, which kind of modeled it or was a close proxy to what was actually required. Similarly, what I believe is that trying to get performance that are akin or in parallel to athletes or in these sports or games is probably a close proxy to the kind of contact-rich loco manipulation task that will eventually lead to the fruitful utility of Lego robots. So this is what I'm aspiring at. And again, as I mentioned, graphics and simulation has always been a guide to robotics. And this is exactly what was done by DeepMind between the years 2017 to 2021. So they started with those goofy walking characters, and they ended up trying to recreate the game of football, where there was this multiple layer of planning and multi-agents and everything intact. So on that note, I'll conclude with a quote that I recently came across, which kind of summarizes Moravec's paradox the best. So the main lesson of 35 years of AI research is that the hard problems are easy and the easy problems are hard. So the mental abilities of a 4-year-old, which we take it for granted. So recognizing a face or walking across the room and things like that are one of the hardest problems. So this kind of flies in the face of the whole assumption in which I started working with RL, where I thought if RL is able to solve Go, probably walking is a piece of cake. But again, I was proved wrong. And secondly, the recent results of DALI that most of you might be familiar with also is consistent with it, where when it comes to challenging cognition, it's rather straightforward. But when it comes to something that we take for granted, like motor skills, it's still quite challenging from an AI perspective. So given the advances in computation, sensors, and actuation, I think the only missing part is algorithms, and that is what I'll be working on. So thanks to all of you for listening, your time, and all my collaborators, without which the work wouldn't have been possible. Amazing people made this. And on that note, this trail is continuing to USC. So my next stop is there, where I'll be starting my PhD under Professor Kwan Nguyen. So yeah, thanks a lot. And yeah, any questions?
Great.